Yes, well, this is sort of high school physics, and which is why scientists find it so infuriating that anybody could deny this. It's like denying gravity or saying that the world is flat. It's because when you think about the Earth as a ball in space, covered with an atmosphere, then the distance that the Earth is from the Sun means that it's absorbing it's receiving a certain amount of radiation from the Sun, shortwave radiation, that warms the Earth up. And then the Earth emits radiation that's a characteristic of its own temperature. So that's infrared radiation. So the Earth is emitting radiation, it's absorbing radiation. The balance between them gives you the temperature of the Earth. Now you add carbon dioxide to the atmosphere, the shortwave radiation from the Sun still reaches the Earth and warms us up, but the radiation that the Earth's emitting is held back by the carbon dioxide. It absorbs those frequencies. It doesn't touch the shortwave, but it absorbs the long wave, and that warms up the atmosphere, and it doesn't get back out into space. So the Earth warms up, and the more carbon dioxide there is, the warmer the Earth is, because the Earth has to have a balance between what comes in and what goes out. And if what goes out isn't going out, the only way you can make it balance again is to heat the Earth up, because then it emits more long wave radiation. So it's inevitable that you add carbon dioxide to the atmosphere, you warm the Earth. I mean, and you can work out how much warming you'll get for each unit of carbon dioxide you add, and so it's very simple physics. It's what you do at high school. It's even pre-university physics. So it's simply not possible to say, oh, the jury, like a lot of politicians do, the jury's out on whether carbon dioxide causes global warming. It's like the jury's out on whether the Earth goes around the Sun. It's that sort of level of mentality. So it's very annoying to see that kind of crap produced by politicians and climate deniers. At the moment, they're a big concern because the greatest single threat of a sudden warming event would be if the methane in the offshore sediments around the Russian Arctic is all emitted in one go, in one short period, because the protective permafrost has melted. That would be a very severe climate threat. It would give us about zero point 0.6 of a degree of warming suddenly. That would be pretty catastrophic. But in the long run, methane oxidizes in the atmosphere, and after about 10 years, any release of methane is lost. The methane, in fact, turns itself into carbon dioxide. But so you can get a really damaging event, but after a few years, there's no trace of it left. And that makes carbon dioxide the bigger threat because of its long-term effects. But methane can do harmful things over the short term, and there's been, because of that, and because the methane then disappears as if it had never been there, there's various events in history, or in the climatic history, where people have started to wonder, was there some sudden outbreak of methane from somewhere that happened that gave us some catastrophic event, where the methane then went away and nobody has any evidence of what happened. So you can if there's a catastrophic event in climate history where you don't know what it was, it's tempting to say, well, that might have been a methane burst. But I don't think one should say that unless you've got evidence for it. Well, I started measuring in 1970, and that was before it really started to retreat. And from then to now, the volume of ice in the summer is a quarter of what it was in 1970. The area is a bit something less than a half, but the thickness is also about a half. So you multiply the two together, you get a quarter. So there's only a quarter as much ice as there was in 1970s. It's amazing, and again, people don't realise it. They sort of think of slow change, and maybe something slow like the Sahara slowly advancing. But when you look at sea ice, it was such a big component of the North, and yet three quarters of it has disappeared. Yes, there's a problem with modelers, which is that they don't look at data, and they work away on their computers and in some research institute, and they're using what they think of as the latest techniques, the best techniques for representing the flow of energy through the ocean ice atmosphere and the equations that represent the interactions. But in practice, they must be wrong, because when you compare those results, which tend to lead to long-term survival of the ice, they don't fit at all what's actually observed. Now that the proper response of a modeler was something like there was a famous dictum by Carl Sagan who said that if you've got a theory, it can be the most beautiful, wonderful theory in the world, but if it doesn't fit the data, then it's wrong. But modelers don't want to accept that. They say, well, if the model doesn't fit the data, then there's something wrong with the data, and I want to keep my model. They don't want to abandon their model. It may have cost quite a lot to develop. Their careers may depend on it. If it's the official model of, say, the meteorological office or NASA Goddard or something, if it's an official model and it's wrong, they don't want to abandon it because that will affect their career prospects. So they persist in saying, well, there might be something wrong with the observations, and I can maybe change the model around a bit. But they don't want to admit that it's wrong. And the people who are most successful at modelling are the people who combine modelling with observation and put in what they see when they go to the Arctic. Like one of the best modelers is Wisław Masłowski, who's at the Naval Postgraduate School in Monterey, and his models are the closest to reality of any of the prediction models for ice extent, and that's because he puts in lots of small-scale effects that you observe near ice edges when the ice is growing or retreating, but which the normal modelers don't know about and don't put in the model. They turn out to be very important, and by putting them in his model, he gets a good fit to the data. In principle, it will, because it will be easier to drill for oil in ice-free waters or in waters with thin ice. So that makes life easier for the oil industry. But we've seen, even though the ice has been retreating from the Beaufort Sea, we've seen Shell, for instance, going out to drill and then giving up. And they say they gave up because of there wasn't a good prospect. But in fact, what seems to have happened is they looked at the cost that they would have to bear if there was a blowout. And if you have a blowout under ice of oil and gas, and it spreads under the ice and the ice carries it all over the Arctic, the cost of cleaning that up is just absolutely massive. And in fact, it really can't be done properly. So Shell were frightened that something would happen to them, as happened to BP, that was almost driven bankrupt by having to pay for the Deepwater Horizon cleanup. So all the studies that have been done of oil spills under ice, including a panel of the National Academy that I was on, have come up with this conclusion that an oil blowout in the Arctic would be massively expensive and very difficult to clean up. So the oil industries looked at that and thought, do we want to run the risk of being told to pay up like BP was, or is it easier just to give up on Arctic oil and go and frack instead? And so far they seem to be giving up on Arctic oil because of I think the fear of the cost of cleanup if there's a blowout. Well, the albedo is the fraction of shortwave radiation that's immediately reflected back out into space. So when we're looking at the energy balance for greenhouse warming, I've said already that the more CO2 there is, the more the outgoing radiation is reduced, and because it's held back. But on the other side of the equation, there's the incoming solar, which isn't held back by CO2, but it is reflected. If you've got a white surface, it doesn't actually heat up the planet. So a white planet is a planet that tends to be colder, and in fact it's cold to start with because it's white, but it's reflecting much more radiation out into space. So a white surface is 80 to 90% reflecting albedo, and a dark surface is less than 10%. So it's a very big difference whether the Earth is dark or white. And at the moment it's white, but it's becoming darker in the high latitudes. Yes, that's correct. I mean, what's happening is that the albedo balance when the sea ice retreats is equivalent to increasing the amount of CO2 that you're putting into the atmosphere by 25%. But if you also consider the retreat of snow on land, which is a similar reduction in area and also replacing light by dark, then that can roughly be said to be about the same as the albedo effect on the sea ice. So add them together and you've got 50%. So that means you're getting the amount of warming you're getting from a given amount of CO2 release is 50% more than you would expect if there wasn't any sea ice around to retreat or any snow to retreat. So the direct warming effect of CO2 is enhanced by 50% by the effects that it's producing on the snow and ice. And that's a pretty big factor, in fact. That the ultimate fear, which I mentioned, but I don't believe it's happening yet, or even maybe that it will, is runaway global warming, where you don't need to have any stimulus. You just get these responses, and I think you can draw an analogy to feedback feedback in electronics, where, for instance, if you were Jimi Hendrix, you could play the guitar without touching the strings and depend entirely on feedback through the amplifier. So it could be that we'll reach the point where there's so much of these effects going on, where the snow and ice are retreating, the albedo's decreasing, the world is warming, and that causes the ice to continue to retreat and the albedo to continue to decrease. And this can all happen without any stimulus from the outside. It could be that it will continue to go on even when we stop adding carbon dioxide to the mix. It's just happening as a self-contained feedback loop, and that's what we would call runaway global warming, because it will happen. We just gaze in horror as it happens. Even if we're not putting any CO2 in, it might happen. Now all of them are. All the major glacial regions of the planet are in retreat. Until about 10 years ago, they were nearly all in retreat, but there was one area where glaciers were advancing, which was in Norway, and it was because Norway had a maritime climate, and because of climate change, Norway was getting more rainfall or snowfall as it fell on the glaciers. And the glaciers were advancing not because they were getting colder, they were in fact getting warmer, but they were receiving more snow. And that caused a temporary surge, and Norwegian glaciers advanced for a while, but now they're retreating as well. So all glaciers are retreating now. Well, the Greenland ice sheet is losing 300 cubic kilometres a year, and the total addition of water to the planet causing sea level rise is about 600, and that means that Greenland alone is responsible for half the extra water that's causing sea level rise. But Antarctica was thought to have no influence, but then using this new satellite gravity instrument, it's now shown to have about 80 to 90 cubic kilometres a year. So it's still only about a third to a quarter of what the Greenland is doing, but it's risen from zero in a very short time. So I think we can, we're still able to use that instrument, which is very accurate, we'll probably see the Antarctic's contribution rising, and therefore the total amount of sea level rise rising as well. Well, it's the Intergovernmental Panel on Climate Change, and it was established in 1990 by a consortium of all the world's leading nations to look at all the evidence for climate change in every area, and what climate change is, what it's doing in the earth, the atmosphere, the ocean, and what it's doing to wildlife, what's it doing to cities and civilization. It's what's it doing everywhere. And it was meant to be an assessment in which we were able to see what global warming is doing to the planet. And it came up with new assessments about every 4 years. The first assessment was 1992, and it was a single volume about this thick. And it was very easy to read. You could lift it as well and carry it about. It was published by Cambridge University Press, and I still find it the most useful assessment because it covered everything in a single volume. And it wasn't subject to political interference, although it was intergovernmental, which meant individual governments contributed. They didn't interfere with the results, and it was led by very good scientists, and so you could trust the results. But then as time went on, firstly, there was much more work being done on global change. So instead of one volume, you now have 4 volumes, and they're really fat, and you can't even lift them. So nobody reads them, because if you can't lift it, and you don't read it, and you just look to see if your paper's in there. And that's been a big problem. And then there's been political interference in the results, because you used to just have this one volume. You read the whole volume, it told you what was happening in climate change. But now, because you have these 4 doorstep volumes, you have thin volumes which summarise the results, the policymakers supplement. And that means there's a lot of political interference at that stage. I mean, the politicians couldn't care if there's sort of 3,000 pages of detailed science. They're not worried about that. But if there's some recommendation in a short report that goes with it, they want to be in there modifying it so that it suits their political interests. So there's massive arguments, and political skullduggery goes on with reference to the summaries and supplements of IPCC. So IPCC has kind of lost its purity, really, by becoming so big, and it's politically interfered with now.